Our goal with SmartGrip is to provide a low-impact way to build and measure grip strength. Our prototype measures the length of a grip squeeze, long versus short, using the pressure sensor on the sensor tile. We use machine learning to differentiate between squeeze types. The main motivation for a project like this is for a therapy setting. A personal motivation of mine, my daughter suffers from cerebral palsy due to a drowning accident, and grip therapy is a big part of her recovery as it helps with the fine motor skills we use for activities like playing and feeding ourselves. So the application of a device like this is huge for families like mine. Let's show you how it works.
For our prototype, we placed the sensor tile and nucleo board inside an airtight plastic container. A couple different containers were tested, and we found that a container with clamped sides was the most effective at being airtight. 3 holes were drilled in the container to run the 2 USB cables and a piece of vinyl tubing. Hot glue was used to fill any gaps around these holes. On the other side of the vinyl tube is a bulb aspirator. This is what the user manipulates to perform the gestures. Originally a balloon was going to be used, but the bulb proved to be much more consistent in varying pressure. To collect our test data, we connected the sensor tile to an Android phone with the STBLE sensor app. For each of the gestures, we ran a 3-minute test. The data for these tests were saved in CSV files and used for model development and statistical analysis. For each grip gesture, we measured the change in pressure during a single squeeze or pinch, and repeated this calculation over each of the 3-minute tests. Our different tests were fist squeeze, 2-finger pinch, 4-finger pinch, index and middle, thumb and pinky. These tests were performed on both dominant and non-dominant hands, and these gestures were inspired by real-world therapy exercises. The data for each test was saved as a CSV file for further analysis. Once we had completed gathering data, we were able to compare the pressure readings across all the tests. The first value that we looked at was the change in pressure during each gesture. You can think of the pressure reading for a single gesture as a pulse. We found the amplitude between the maximum and minimum and recorded this for each pulse. Very early in this process, it was clear that some of the gestures had very similar results. Because of this, we decided to focus only on the fist squeeze and the 2-finger pinch. We also did not see much of a difference between the dominant and non-dominant hand, and decided to focus solely on the performance of the dominant hand for further analysis. We performed this calculation in Google Sheets so we could visually see where each pulse was being recognized. After we had all the amplitudes calculated for our decided gestures, we performed a statistical analysis. We calculated the mean, standard deviation, and quartiles, as well as display the distribution. This analysis was performed for both short and long gestures. For short gestures, we only had to consider a short pulse with 1 amplitude calculation. For long gestures, the amplitude calculation was taken twice, once during the rising edge of the pulse and again during the falling edge. For the long gestures, there was some loss of pressure over the 5-second duration, and this was normal. To account for this, the same statistical analysis was performed for this drop in pressure as well.
This is Isabelle, and I'll cover the steps we took to train and deploy a machine learning model in the cloud to classify the squeezes in long and short movements. Why cloud? We decided to take this approach for a couple of reasons. Here we compare a model hosted in the cloud versus a model hosted in a firmware or application. When a model is in the cloud, the application is sending the data from the sensor to the cloud and getting a response back. Therefore, if the model is updated in the cloud, all users will have the same version, which can be updated anytime. Also, even though we would need internet for the most updated version, if there's no internet, a copy of the model can be hosted in the firmware. Also, thinking further, cloud providers can deliver scalability. Cloud is not as cheap though. Regarding data preparation, our main concerns were about atmospheric pressure, time interval, and data cleaning. The barometric pressure is the atmospheric pressure. As we can see here in the last column, all pressures are over 1,000. So the data was collected in a place where the atmospheric pressure was about 1,000 in bars. While building the model, we assumed an atmospheric pressure of about 1,000. So when the read is 1,070, it means a squeeze pressure of 70. But for the app, we first removed the atmospheric pressure so the app can work in any location. Regarding the time interval, first we tried using a 5-second average, but there was some overlapping averages. Then we took the approach of a 10-second average, which gave us different values for long and short. Short movements averages at around 35 in bars, but the averages ranged from about 28 to 40. For long movements, the average was around 45, but the averages ranged from 40 to 55. There's almost an overlap this time, but not quite. Regarding cleaning data, it was not really necessary. When we collected the data, there was always some pressure happening, right? And we also collected the necessary data that we were going to use. Now for the model training on Azure. This is the pipeline for the model that I'm going to explain in detail. From the full data set, which was 100 averages, we had 50 longs and 50 shorts. So we randomly split the data in 60-40, being 60 for the training data and 40 for the test data. Now about the algorithm used in the model. This is a two-class averaged perceptron, which is a very simple version of a neural network. The inputs are classified into possible outputs based on a linear function. The inputs are then combined with a set of weights from the feature vector, hence the name perceptron. Now for the model test on Azure. Here you can see the test scores. There are the pressure, the correct classification, the predicted classification, and the certainty level. As we can see in line 5, when the pressure was about 37.8, this was a short movement, but the model labeled as long, with a probability of around 46%. But overall, the model performed correctly on most cases. Here we can see that the accuracy is 85%, and the comparison between predicted versus actual is pretty good, with all the long movements predicted correctly and about 2/3 of the short movements predicted correctly. Here let's see about the model deployment. The model was deployed in a Docker container on Azure. The deployed model is wrapped in a REST API. This way, all devices and applications that have the key to the REST API can call the model through the web. Our model in the cloud is called by our app to classify the squeezes. Now for the model use. When the model is called, it sends a JSON response. Here we can see the first response that when the movement is very easy to identify, being a short in bars, for example, the certainty level is high at about 83%. However, when the movement is in a gray area, in this case a pressure of 40, it predicted correctly that it's a long movement, but the certainty level is smaller at about 39.
We use Jupyter Notebooks to loop through a REST API that calls the Azure Machine Learning Model. The sensor tile outputs an average pressure value taken in 10-second increments. The Jupyter Notebook uses Python code to receive the average value as serial data and send it to the model. Looking at the squeeze gesture, we can classify a short exercise and a long exercise.
For future work, we can explore different pressure standards based on age, gender, and disability using these new features to retrain the model over time. We can also update our prototype, adding in a sensor glove that could correctly identify pinch and grip gestures. We could use this data to fine-tune our model or explore other models, such as the support vector classifier. And finally, we can gamify our app, adding in games such as racing or navigating a maze based on grip pressure. This would make therapy more fun and engaging.